Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Now we are going to start 14 group elements, that is P block elements. In this lecture, we are going to discuss about 14 group elements. So please listen carefully, all of you. It's very important chapter. Let us start now. 14 group elements. So group 13 we have discussed already. Next, we are going to discuss now 14 group elements. After this, we are going to discuss additional points in group 13 and 14 and questions followed by it. Now coming to group 14 elements, carbon family. It is also called as carbon family. Carbon family or group 14 comprises of carbon, silicon, germanium, tin, and lead. These elements have general electronic configuration of NS2 and P2, two electrons in P subshell, two electrons in S subshell. So their individual electronic configuration are as follows. Carbon atomic number is 6, so helium 2s2p2, silicon atomic number is 14, so neon 3s3p2, germanium atomic number is 32, argon 3d10 4s4p2, so tin, so here I'm writing atomic number 6, silicon 14, germanium 32, and tin atomic number is 50, 50. That's why it's krypton 4d10 5s2 5p2, and lead, very important lead here. Lead is radioactive also, and atomic number is 82. It is 4f14 5d10 6s2 6p2, 6s2 and 6p2. So xenon, the noble gas configuration is xenon. So 4a14, 5d10, 6s2, 6p2. This is 6p2. Please make a note change. So these are the electronic configurations of these group elements. The outermost configuration is ns2, np2. So if you see 2s to 2p2, 3s to 3p2, 4s to 4p2, 5s to 5p2, and 6s to 6p2. These are the outermost electronic configurations of 14 group elements. Next continuation. Occurrence. Carbon is the 17th and silicon is second most abundant element. As I told you, oxygen is first most abundant element, second is silicon. Silicon in the form of sand. So carbon is 17th and silicon is the second most abundant elements by mass in Earth's crust. First most abundant element is oxygen. Oxygen is the first most abundant element. So next we have silicon. Next we have aluminium is the third most abundant element in the Earth's crust. Carbon is available in free as well as in combined state. In elemental form, it is available as coal, graphite, and diamond. That's why, since carbon is forming many allotropes, its study has been separated based on carbon. So carbon compounds will study separately in organic chemistry. So carbon compounds we are studying separately in organic chemistry, and carbon is available in free as well as in combined state. In elemental form, it is available as coal. Coal is nothing but amorphous form of carbon. Graphite crystalline form of carbon. Diamond is a crystalline form of carbon. So coal is the amorphous form of carbon. Form of carbon. Coal is nothing but amorphous form of carbon, and diamond, graphite, and diamond are crystalline forms of carbon. Crystalline, they exist as crystals, crystalline form of carbon. So in combined state, it is present as metal carbonates, that is sodium carbonate, etc. Hydrocarbons, that is carbon compound, that is methane, etc. And carbon dioxide. Carbon contains two stable isotopes, carbon 12 and carbon 14. This is carbon 14. So carbon 14 is a radioactive isotope of carbon available and useful in carbon dating to determine age of fossil fuels. And half-life of carbon 14 is 5,770 years. So this way, this carbon 14 is used for determining age of fossil fuels, and carbon 12 which we are using regularly. So this carbon 12 isotope is based on all the atomic masses are compared to carbon 12 isotopes. All the atomic masses are compared of all the elements in the periodic table are compared with respect to carbon 12 isotope. So carbon has two isotopes mainly, carbon 12 and carbon 14. Carbon 14 is a radioactive isotope of carbon available and useful in carbon dating to determine age of fossil fuels. So half-life of carbon 14 isotope is 5,770 years. And what are the crystalline forms of carbon? Coal. And sorry, amorphous form of carbon is coal, and crystalline forms of carbon is Allotropes of carbon is graphite and diamond. So please make a note of all this. However, we'll study in this chapter silicon, more about silicon, not about carbon, because carbon study anyway we are going to do in organic chemistry. Silicon is mainly present in nature as silica and silicates. So next we are going to discuss about occurrence of silicon. Silicon is the second most abundant element in the Earth's crust. It is in the present in the form of sand. So you can see everywhere sand here. So silicon dioxide is nothing but sand only. So silicon is mainly present in nature as silica and silicates. Silica is nothing but sands. And germanium is available only in traces of silver, zinc ores, and some types of coal. So germanium is a semiconductor. It is used as semiconductor. It is a metalloid. Tin occurs as cassiterite ore, that is SnO2, tin dioxide, and lead as galena, PbS ore. Carbon can form innumerable compounds due to its maximum catenation capacity. What is catenation? Catenation capacity. That catenation is nothing but the property of forming long chains, branch chains, long chains, long straight chain, branched chains, branched chains, and the ring structure. So the carbon compounds can have the ability, tendency to form long straight chains, branched chains, and ring structures in the form of like benzene. You can see benzene here, C6H6. So etc. That's why it is having maximum catenation capacity, maximum catenation capacity. So the entire periodic table, the maximum catenation capacity is for carbon only. And in this group, carbon and silicon are nonmetals, whereas germanium is metalloid. Tin occurs as metal, and galena, lead also metal. So here I write carbon and silicon nonmetals. Germanium is metalloid. That's why it is used as semiconductors. And tin and lead are metals. So in this group we have two non-metals, two metals, and one metalloid. So this is the introduction of these 14 group elements. So out of all the elements in the periodic table, which has maximum catenation capacity, what is catenation capacity? The tendency of forming long straight chains, branch chains, or ring structures is called as catenation. So maximum catenation capacity is for carbon, second catenation capacity is for silicon. So in the entire periodic table, the catenation capacity is present only for this group elements only, that is carbon and silicon. First we have carbon. Carbon will form due to its catenation capacity. Carbon will form millions and millions of compounds, whereas silicon will form limited number of compounds. So I can write here the statement due to catenation, property, carbon can form millions of compounds, and silicon also forms limited number of compounds due to catenation capacity. Limited number of compounds. So this catenation capacity will be existing for carbon and silicon alone. First highest capacity is for carbon, next we have silicon in the entire periodic table. That's why as carbon is forming millions and millions of compounds, its study is kept separately. That's why it is called organic chemistry. So carbon compounds, more about carbon compounds we'll study in organic chemistry, and silicon we'll study in this chapter as I told you. So in this group we have two metals, two non-metals, and one metalloid. What is the metalloid in this group? That is germanium. Next continuation. So minerals of carbon, calcium carbonate, citrate, magnesium carbonate, dolomite. Dolomite is nothing but magnesium carbonate, calcium carbonate, etc. These are the main ores of carbon. Next, general characteristics. So general physical and chemical properties we are going to study now. For group 14 elements, the covalent radius increases down the group from carbon to lead. Covalent radius increases down the group from carbon to lead. So covalent radius, carbon 77, silicon 118, germanium 122, tin 140, lead is 146. This is called covalent radius. What is covalent radius? Covalent bond formation. So this is called covalent radius. First point. Second point, ionization enthalpy. It is very interesting to see ionization enthalpy here. Group 14 elements have higher ionization enthalpies than corresponding group 13 elements. From carbon to tin down the group, the value of ionization enthalpy decreases because of the increase in atomic number. The slight increase in first ionization enthalpy from tin to lead is due to the poor shielding effect of D and F electrons in lead. Due to the poor shielding effect of D and F electrons in lead. So that's why the order changes like this. Ionization enthalpy order, first ionization enthalpy of group 14 elements. First ionization enthalpy of group 14 elements, please note it down because it is not following a regular trend, it is following different trend. So you can see here carbon greater than silicon, greater than germanium, greater than lead, greater than tin. So lead is greater than tin. Tin is the least one. Why lead is having more? Due to the poor shielding effect of D and F electrons. And in lead, what is present here, if you see the configuration of lead, it has fully filled F orbitals and fully filled D orbitals, 4F14 and 5D10 for lead, 6s2, 6p2, 6s2, 6p2. So this is the configuration of lead. So due to the due to the fully filled 4F electrons and 5D electrons of tin, it is having poor shielding effect, due to which what happens, the nuclear charge increases, the outer electrons will be coming closer to the nucleus, and due to the poor shielding of 4F and 5D, the outer electron, that is 6s2 and 6p2, will be under nuclear attraction. So to remove these electrons, high energy is required. So that's why the first ionization enthalpy for lead is greater than tin due to poor shielding effect of D and F electrons of lead. So due to this, what happens? Lead contains 4F14, 5D10, 6s2, 6p2 configuration. So 4F14 means completely filled F electrons and completely filled D electrons. Due to poor shielding effect of D and F electrons, these outer electrons, that is 6s2, 6p2, will be under the nuclear attraction. So nuclear charge increases. As a nuclear charge increases, ionization enthalpy also increases. So the ionization enthalpy for 14 group elements follows the order: carbon greater than silicon, greater than germanium, greater than lead, greater than tin. So this is the variation of ionization enthalpy. Please make a note of it. Very, very important in your classwork because these orders they'll ask in the examination. So when compared to group 14 elements, group 13 elements have lower ionization enthalpies. So group 14 elements have higher enthalpies than corresponding group 13 elements. So group 13 elements is having less ionization enthalpy when compared to group 14 elements within the period. Next continuation. Ionization enthalpy continue. You can see here first ionization enthalpy for carbon it is 1086. Here I write the element also. Element is carbon, then silicon, then germanium, then lead, sorry, tin, and then lead. Lead is highest than tin because of poor shielding effect of D and F electrons. So second ionization enthalpy 2352, 1577, 1537, 1411. For this, no second ionization enthalpy. And third ionization enthalpy, because lead is radioactive, so we cannot say. Next, third ionization enthalpy, these are the values. Fourth ionization enthalpy, these are the values. So the order of ionization enthalpy is carbon greater than silicon, greater than germanium, greater than lead, greater than tin. So this order is very, very important. Please make a note. Next continuation. Electronegativity. Next point is electronegativity. Elements of group 14 are more electronegative than the corresponding group 13 elements. First, elements of group 14 are having more electronegative. So here I write the statement: elements of group 14, elements of group 14 have more electronegativity values than corresponding group 13 elements. Than corresponding, the word corresponding is important here. We can compare with the same period elements corresponding group 13 elements. group 13 elements, corresponding group 13 elements. So due to their small size, the electronegativity, however, decreases from carbon to silicon. Carbon is the element with highest electronegativity among these elements with a value of 2.5. The electronegativity values for other elements are almost the same. So the electronegativity value from decreases from carbon to silicon. It decreases from carbon to silicon, decreases from carbon to silicon, then and remains constant for silicon to tin. Remains constant, remains constant from silicon to tin and slightly increases for lead. Slightly increases, sorry, sorry, slightly increases for lead due to effective nuclear charge, increase in effective nuclear charge. Due to increase in effective nuclear charge, it slightly increases for lead. So the electronegativity values, however, decreases from carbon to silicon and remains constant from silicon to tin and then slightly increases for lead. This is due to filling of d orbitals in germanium tin and both d and f orbitals in lead. So germanium and tin due to d orbitals and for lead it is due to d and f orbitals. So as d and f orbitals are offering poor shielding effect. So due to effective nuclear charge, due to increase in effective nuclear charge, due to increase in effective nuclear charge, increase in effective nuclear charge, the ionization electronegativity is more for lead in effective nuclear charge. Effective nuclear charge. As effective nuclear charge increases, electronegativity character also increases. So electronegativity increases. So please make a note of all these points. It's very important. So carbon is the element with highest electronegativity among these elements with a value of 2.5. Next we have silicon. So from carbon to silicon it decreases and it remains constant from silicon to tin. Why it is remain constant? Due to d and d orbitals. Due to d orbitals of lead, germanium and tin. Due to d orbitals of germanium and tin. Because in germanium and tin we have only d orbitals and for lead, we have d and f orbitals. Due to poor shielding effect of d and f orbitals, the increase in effective nuclear charge increases. So, in effective nuclear charge increases, due to which what happens? Electronegativity character also increases. So, the trend is carbon greater than silicon, silicon greater than germanium equal to tin, constant greater than, sorry, less than lead. So greater than germanium is equal to tin is equal to less than lead. Lead is having more when compared to germanium and silicon. Sorry, tin. So straight away we can write decreasing order means carbon, silicon, lead, germanium equivalent to tin. This is the final order. So I hope you understood why it is having more for lead because of effective nuclear charge. Increase in effective nuclear charge due to the poor shielding effect of d and f electrons in lead makes it more electronegative. Next continuation, physical properties. So group 14 elements are all solids. First important point, they are all solids. Carbon, silicon are non-metals as I already told you. Germany is metalloid and tin and lead are metals. Melting points and boiling points of these elements are very high. So down the group, the melting metallic character increases. Carbon and silicon are non-metals. Germany is metalloid. So the change from non-metallic character to metallic character is due to less effective nuclear charge. So continuation now. So the melting point and boiling points of carbon and silicon, you can see the melting points and boiling points of group 14 elements are much higher than those of corresponding group 13 elements. So melting points is more, melting points and boiling points are higher than corresponding group 13 elements. Corresponding group 13 elements. Because in group 13 elements we have solid liquids also, but here all are solids. So you can see here the melting point of carbon 4373 kelvins, silicon 1693, germanium 1218, tin 505, and lead is slightly increasing. For lead it is 600 again. So the melting point and boiling point decreases down the group. However, the melting point of tin is lower than that of lead. This is due to corresponding decrease in the interatomic force of attraction, interatomic forces. So due to interatomic force of attraction for lead, it is more for lead when compared to tin. Similarly, you can see second boiling point, it follows the order. Carbon do not have any boiling point because it's very, very high. So we cannot change carbon into gas because carbon exists as solid. So 3550 kelvins, 3123, 2896, 2024. So only melting point is increasing for lead. Why it is increasing for lead? This is due to it has lead is having extremely more when compared to tin. This is due to decrease in the interatomic force of attraction. Decrease in the interatomic force of attraction. Interatomic forces of attraction in tin. Force of attraction in tin. So if it is not clear, please make a note. Decrease in the interatomic forces of attraction in tin. Its melting point is lesser when compared to lead. So the order for melting points is carbon greater than silicon, greater than germanium, greater than tin, sorry, greater than lead, greater than tin. Tin is having least. So these orders definitely they'll ask. Wherever you have exceptions, that exceptions are very important for the examination point of view, entrance exams. They'll ask exceptions, exceptional orders only. So melting points and boiling points are higher than those of corresponding group 13 elements. Next continuation. Chemical properties. Oxidation states. So the general oxygen states of these elements are +2 and +4. Carbon can also exhibit negative oxygen states. Compounds of these elements to their +4 oxygen state are covalent as some of their first four ionization enthalpies is very high. So carbon can exhibit +2. So carbon dioxide, if we take into consideration, it is exhibiting +4. Carbon monoxide +2. And carbon dioxide, carbon monoxide. And methane, it is -4. In case of methane, it is -4. So carbon can exhibit both positive and negative oxygen states. So if you see the carbon compounds like this we have. Next we have carbon dioxide, carbon monoxide like this. And the general oxygen state of these elements are +2 and +4. +2 and +4. So lead exists as lead oxide +2 state. Lead dioxide +4 state. Tin oxide +2 state. Tin dioxide +4 state. So for lead, tin, germanium only +2 and +4. For carbon, silicon also +2 and +4. Silicon dioxide it is +4. Silicon carbide it is +4 like this. So silicon, germanium, tin, and lead will undergo only +2 and +4 oxygen state, whereas carbon can also exhibit negative oxygen states with respect to hydrogens. Compounds compounds of these elements to the +4 oxygen state are covalent. So +4 oxygen state compounds are covalent. So lead dioxide is covalent, whereas lead oxide is ionic. Because of metallic and non-metallic character, it is ionic. Tin dioxide is covalent, whereas tin oxide is ionic. So +4 state oxygen state are covalent as some of their first four ionization enthalpies is very high, and +2 state oxygen states, that is only for tin and lead. +2 oxygen states for tin and lead compounds are ionic, and they are moreover basic also. Ionic compounds, and moreover they are moreover what basic compounds also. So that is the trend of oxidation states. So oxidation states trend is very, very important. So oxidation states and chemical reactivity. the high sum of total first four ionization enthalpies, that is ionization energy 1. So IE1, that is ionization energy 1 plus IE2 plus IE3 plus fourth ionization energy IE4 is equal to very high, not compared. So that's why the highest sum of total first four ionization enthalpies are more. So C4 plus ion does not exist due to following reasons, whereas carbon plus four state exists actually. So as some of their first four, these are covalent. Compounds of these elements to their plus four oxygen state are covalent as their first ionization, four ionization enthalpies is very high. That's why these compounds are covalent. So please make a note of this. So examples of carbonates containing carbon forms carbide, stellate, and halide. So carbon can exhibit negative oxygen states also, whereas other elements in this group exhibits only positive oxygen state with plus two and plus four oxygen states only. Plus two as well as plus four. Plus two as well as plus four mainly. So these are the common oxygen states exhibited by this element. What are the common oxygen states? Plus 2 and plus 4 for all the elements. And for carbon, it can exhibit even negative oxygen state also because of its high electronegativity. Carbon in certain compounds can exhibit negative oxygen state also. And the plus 4 oxygen states of all these elements, compounds are covalent in nature as their sum of their first four ionization enthalpies is very high. That's why they are covalent in nature. For example, lead dioxide is covalent, tin oxide tin dioxide is covalent, whereas lead oxide PbO in plus 2 state is ionic. Tin oxide in plus 2 state it is ionic. Ionic compounds as well as covalent compounds. Next continuation. So oxygen state due to inert pair effect, very important. Here also, as I told you, inert pair effect plays a key role in p block elements. For all p block elements, inert pair effect exists. Due to inert pair effect down the group, the tendency to exhibit plus 2 oxygen state increases. So lead is more stable in plus 2 than plus 4. Lead is more stable than in plus 2 than plus 4. However, germanium and tin, germanium plus 4 state is more stable. Tin also plus 4 state is more stable. And silicon also plus 4 state is more stable than plus 2 state. Greater, more stable than plus 2 state. Whereas lead alone is plus 2 state is more stable than lead plus 4 state. So the stability of order of plus 2 oxygen state is germanium less than tin less than lead. So tin is lead is more. The compounds of tin in plus 2 oxygen state acts as reducing agents because they are ionic in nature. They can act as reducing agents. So tin oxide is reducing tin chloride, SnCl2. These are all plus 2 oxygen states. So these are strong reducing agents. Compounds of lead with plus 4 oxygen state acts as strong oxidizing agents because of covalent character. Covalent character, they are acting as oxidizing agents. Oxidizing agents. Very important points. And inert pair effect is more due to the inert pair effect. What is inert pair effect? As we discussed in the previous class also, the reluctance of s electrons. Reluctance of s electrons in bonding. Reluctance of non-involvement of. That is reluctance of s electrons in bonding. S electrons in bonding is commonly called as inert pair effect. So if you take into configuration NH2, NP2, and due to the poor shielding effect of s electrons will be closer to the nucleus, so only p electrons will be involved. So only plus 2 state, whereas plus 4 state means s electrons also should remove. But plus 4 state also can be possible, but it is covalent and it is oxidizing in nature. So if you remove 2 electrons, it is plus 2 state. If you remove 4 electrons, it is plus 4 state. So 4 electrons means s electrons are also going off. So inert pair effect is maximum in case of lead. The inert pair effect is maximum in case of lead. That's why lead in plus 2 state is more stable than plus 4 state. So PbO2 is less stable when compared to PbO. So, and moreover, PbO2 is covalent in nature and it is acting as strong oxidizing agent. Strong oxidizing agent. So please make a note of all these things. Very important concepts. The stability of plus 2 oxygen state is germanium less than tin less than lead. Compounds of tin plus 2 oxygen state acts as reducing agents and compounds of lead with plus 4 oxygen state acts as strong oxidizing agents. So all these PPDs you make a note in your classwork, then only you can understand, you can apply the concept in the answers in the exam entrance examinations. Next, chemical properties. So first we have chemical properties. So germanium, before going to this, germanium, tin and lead can show two different oxygen states, that is plus 2 and plus 4. So these elements in plus 4 oxygen state behave as oxidizing agents, whereas in plus 2 it behaves as reducing agents. So germanium, silicon, lead are in plus 2 state reducing agents, and in plus 4 state they are oxidizing agents. So examples for that also I can make a note. Let's see here now. So here I write the important point. So germanium, tin and lead in plus 2 state are reducing agents, and in plus 4 state they are oxidizing agents. So example you can see here, PbO2 plus 4HCl, PbO2 plus 4 moles of HCl concentrated, it changes to PbCl2 plus Cl2 plus 2H2O. So here lead dioxide is bringing reduction in HCl, is bringing oxidation to chlorine gas. So oxidation to chlorine and forms chlorine molecule along with water, and oxidation to hydrogen also. So that's why it is called reducing agent. So sorry, oxidizing agent. Oxidizing agent. Oxidizing agent. Similarly, reducing agent nature, if you take into consideration, so germanium plus 2, lead plus 2, tin plus 2 in plus 2 state are reducing agents, and the plus 4 state they are oxidizing agents. So here chlorine is undergoing here -1, and here it is 0, and here it is -1. So, and hydrogen, for hydrogen oxygen is added, and for chlorine hydrogen is removed. So oxidation reaction. Next continuation. Now, chemical properties of 14th group elements, reactivity with oxygen. All these elements, that is carbon, silicon, germanium, tin, and lead, react with oxygen upon heating directly to form oxides of type EO and EO2. EO is plus 2 state, and EO2 is plus 4 state. EO2 types of oxides are more acidic than EO type, and moreover, they are covalent in nature. And EO type oxides are ionic in nature, and EO2 type oxides are covalent in nature. In dioxides, carbon dioxide, silicon dioxide, germanium dioxide are acidic. So carbon in plus 4 state, silicon in plus 4 state, and germanium also in plus 4 state. These are acidic oxides. Tin dioxide, lead dioxide are amphoteric in nature. So tin in plus 4 state and lead dioxide in plus 4 state, they are amphoteric in nature. So please make a note of this. Definitely they ask which of the following are amphoteric, which are the following are acidic oxides. Acidic oxides means carbon dioxide, silicon dioxide, germanium dioxide are acidic. Tin dioxide, lead dioxide are amphoteric in nature. Among monoxide, that is silicon oxide, exists only at high temperature. Carbon monoxide is neutral. So carbon monoxide, carbon in plus 2 state is neutral. Germanium oxide is acidic, and tin oxide and lead oxide are amphoteric. So however, the oxides of tin and lead are amphoteric in nature in both plus 2 state and plus 4 state, because tin plus 2 state and lead also plus 2 state. So the oxides of tin and lead are amphoteric both in plus 2 as well as in plus 4. They are amphoteric in nature. And the oxides of carbon monoxide is neutral. Silicon monoxide is also acidic, and germanium oxide is acidic. Germanium oxide is also acidic. So germanium in both its oxygen states, that is plus 2 and plus 4, they are acidic oxides. And carbon dioxide is acidic, silicon dioxide is acidic, whereas carbon monoxide is neutral. Carbon monoxide is what? Neutral. So which of the following is neutral oxide? Neutral oxide means carbon monoxide. Please make a note. Carbon monoxide is neutral oxide, whereas carbon dioxide is acidic oxide. So all these elements react with oxygen upon heating directly to form oxides of type EO and EO2. EO2 types oxides are more acidic than EO type. EO means plus 2 state, and EO2 is plus 4 state. Reactivity towards water. So chemical properties, reactivity towards water. Silicon, germanium, and lead are unaffected by water. These are unaffected, means water will not combine with silicon, germanium, and lead. But in tin decompose steam to form its dioxide, only steam, means water in steam form, along with dihydrogen gas. So it forms tin dioxide along with hydrogen gas. Red hot coke, when exposed to steam, it forms a mixture of carbon monoxide and dihydrogen gas. So red hot coke, when mixed with steam, it forms syngas or water gas. It is a combination of carbon monoxide and hydrogen gas. The combination of carbon monoxide and hydrogen gas together, they are called as water gas or syngas, synthesis gas. Very important this reaction. So at very high temperature. So tin, sorry, silicon, germanium, and lead are unaffected by water. They will not combine with water. Only tin with steam only it will combine and forms tin dioxide along with hydrogen gas. And carbon also can combine. Red hot coke. Red hot coke combines with water and forms carbon monoxide and hydrogen gas. A mixture of carbon monoxide and hydrogen gas, which is called as commonly called as water gas or tin gas, syngas. Next, if air is employed instead of steam, if air is employed instead of steam, we obtain a mixture of carbon monoxide and dinitrogen as producer gas. So if carbon is treated with air, it forms at a very high temperature, it forms producer gas. It is also fuel gas. So producer gas is a mixture of carbon monoxide and nitrogen gas. So water gas, producer gas. Combinations are very important in the examination. So producer gas is nothing but combination of carbon monoxide as well as nitrogen gas. Carbon monoxide as well as nitrogen gas. So that is called producer gas. Next, reactivity towards halogens. So reactivity towards halogens. Group 14 elements react with halogens directly to form halides of type MX4. Carbon do not react directly. Germanium, tin, sorry, this is tin and lead even form dihalides of type MX2. So germanium dichloride also it form tin dichloride and lead dichloride, that is PbCl. So it can form halides of type MX2 and also MX4. All MX4 type of halides are covalent in nature except for SNF4 and PbF4 because fluorine is more electronegative. They are ionic. So please make a note. This exception is very important. Usually all MX4 type halides are covalent in nature except for tin tetrafluoride and lead tetrafluoride. These are ionic in nature. In these halides, the central metal atom undergoes sp3 hybridization. In MX4 type, the central metal atom undergoes what? sp3 hybridization and our tetrahedral. PbI4 does not exist because of lead is also big size and iodine is also small, heavier size. So this does not exist because due to large size of cation and anion. Due to large size of cation and anion, they do not exist because and the atomic number is very high and iodine also very high. So it is not possible to form compound of lead tetraiodide. Lead tetrachloride is formed, but lead tetrabromide is also formed, but lead tetraiodide is not formed again. So lead PbI4 does not exist. Which of the following does not exist means PbI4. So these exceptions are very, very important. Make a note of this because they'll ask in the examination exceptions only from this chapter, not only this chapter, from all the inorganic chemistry topics. So in these halides, the central metal atom undergoes sp3 hybridization and SnF4 and PbF4 are ionic because fluorine is most electronegative atom and tin and lead are electropositive. So automatically they form ionic compounds and rest of all they form MX4 and these MX4 type of halides are covalent in nature. So PbCl4 is covalent. PbBr4 is also covalent. PbI4 does not exist at all because of large size of cation and anion. So PbBr4 and PbI4 are not known. The non-existence of PbI4 can be due to strong oxidizing power of lead and strong oxidizing power of iodine. Next, continuation. So these are the important points regarding halides. Carbon does not form any halides. So the directly CCl4 it will form, but it is not directly formed. Carbon cannot combine with chlorine directly. It will form by the means of methane gas. So reactivity of halogens, the thermal stability of tetrahalides, thermal stability order decreases down the curve. So this is the thermal stability order, that is CCl4 greater than SCl4, sorry SaCl4 greater than germanium Cl4 greater than, example I'm giving. So tin Cl4 greater than lead Cl4. So this is the thermal stability order of tetrahalides. GeX2, that is dihalide, is less stable than tetrahalides, and lead X2 is more stable than PbX4 due to inert pair effect. So lead dichloride is more stable than lead tetrachloride. Why? Because due to inert pair effect. Due to inert pair effect. That's why as I already told you, lead in plus 2 is more stable than plus 4. So the oxygen state of lead in plus 2 here, and it is plus 4. So it is due to inert pair effect. Plus 2 state of lead is more stable than plus 4. Whereas for germanium, plus 2 is less stable than plus 4. And all these tetrahalides except CCl4 can undergo hydrolysis by accommodating electron pair of oxygen water molecules, thus forming MOH4 type. So these tetrahalides like PbCl4 on hydrolysis forms PbOH taken 4 times lead hydroxide. So all these tetrahalides except CCl4 can undergo hydrolysis by accommodating electron pair of oxygen atom in water molecules, thus forming MOH taken 4 times. So these are the oxygen states and reactive towards halogens. Next continuation. Reactive towards hydrogen. Group 14 elements react with hydrogen and form hydrides as CH4, SiH4, GeH4, SNH4, PbH4. Also tin hydride and lead hydride, dihydrate, that is plus 2 state apart from this. But germanium, silicon and carbon will form only plus 4 state. Hydrides of carbon are hydrocarbons. Hydrates of silicon are called silanes. Very, very important. Hydrates of silicon are silanes. Hydrocarbons do not hydrolysis due to absence of vacant orbitals, while silanes are most readily easily hydrolyzed as they are least stable. So silanes on hydrolysis forms H2SiO3, that is silicic acid, along with hydrogen. This is called silicic acid. So carbon is not readily hydrolyzed. Here carbon oxygen state is -4. Silicon oxygen state is also -4. Germanium is +4, +4, and +4. Next continuation. So silanes are good reducing agents also. They are good reducing agents. Stability and boiling point of hydrates decreases from carbon to lead. Carbon, CH4, SiH4, germanium, and SNH4. So, and lead also, greater than lead, PbH4. Next, reactivity towards acids and alkalis. Carbon and silicon do not react with HCl. Carbon and silicon do not react with dilute acids. Germanium is not attacked by dilute HCl. With constant HCl, it will attack. Lead and tin dissolves in dilute HCl. So concentrated nitric acid and concentrated sulfuric acid. Concentrated sulfuric acid and nitric acid dissolve germanium, tin, and lead. So tin combines with HCl and forms SnCl2 hydrogen gas. Lead combines with HCl and forms PbCl2 and hydrogen gas. PbCl2 combines with HCl and forms H2PbCl4. So these are the important reactions of alkalis and acids. So now we have seen only alkali acids. Next we'll see alkalis also. And very important point is carbon and silicon do not react with HCl gas, HCl acid. Germanium is not attacked by dilute HCl. It is attacked only by concentrated HCl. Whereas tin and lead dissolves in HCl gas, HCl acid. So carbon is unaffected by alkalis also. So carbon is not affected by acids and alkalis. Silicon reacts slowly with aqueous NaOH in cold and readily with hot aqueous NaOH. So alkalis means soluble bases, that is sodium hydroxide, potassium hydroxide, etc. Tin and lead readily reacts with alto alkalis and form their respective sodium tinnate, sodium lead plumbate, sodium tinnate plus hydrogen gas. So tin on reaction sodium hydroxide plus water, it forms Na2SNO3. It is called sodium stannate. Sodium stannate, and this is called sodium plumbate. Sodium plumbate. Germanium will not combine. Next, silicon tetrachloride undergoes hydrolysis, leading to the formation of silicon OH taken force as shown here. So silicon tetrachloride on reaction with water. So oxygen is donating its lone pair of electrons to silicon, due to which it forms silicon Cl OH. One silicon, one chlorine will go up, and place of that OH will come. Second case, it forms all the Cls will go up and forms OH. So three molecules of water minus three HCl. So due to hydrolysis, those halides can form complex ions like SAF6 2 minus, GeCl6 2 minus, SnOH taken 6 times 2 minus, to which central atom undergoes sp3d2 hybridization. Very, very important. The covalence is 6 here, 6 and 6. So as the covalence is 6, so it will undergo sp3d2 hybridization. So coordination number is also 6. Coordination number in these complex compounds of central metal atom is 6, because they are surrounded with 6 halogens. Is 6. So that's why they undergoes sp3d2 hybridization, and shape is octahedral. Shape is what? Octahedral. So if n factor is equal to 6, so it undergoes automatically. If n factor is 6, it undergoes automatically sp3d2 hybridization. sp3d2 hybridization. Next, continuation. Now let us see some examples. The following are some statements regarding group 14 elements. On moving down the group, the metallic character increases. Yes. The ionization enthalpy decreases. Yes. For lead, it increases. The stability of +2 oxygen state increases. The atomic radius decreases. So that stability of +2 oxygen state increases. Correct. The atomic radius decreases. The atomic radius decreases because the distance between center atomic radius increases actually. The correct statements are, so what are the correct statements? Easily you can tell the answer. It is A, that is 1, 2, and 3. Because you can see here, first statement, the metallic character increases, correct one, the ionization enthalpy decreases, correct one, third one, the stability of +2 oxygen state increases. Here some small exception is there, lead increases. But the atomic radius decreases is wrong, because atomic radius always increases. So this is answer is first option. Next question. Carbon has valency of 4 in CH4. Its valency is still in is. Its valency is still. What is the formula of in C2H2? Covalency is how much? So C2H2 carbons are indicated by triple bonds. This is the structure. Acetylene. Acetylene is this. Acetylene gas. So now we can see the answer. Covalence is 4 again, because triple bonds are anywhere carbon valence is 4 in all organic compounds. In all organic compounds, carbon valency is 4. You can write a statement: in all organic compounds, in all compounds, simply you can say the valency of carbon is 4. The valency of carbon is 4. Very important point. Next question. The ionic chloride is, see here, ionic chloride they are asking. So +4 state, +4 state. Lead is also +4 state, but here it is +2 state. So lead in +2 state, it is ionic in nature. So answer is D option. As I told you, lead in +2 state, it is ionic in nature. +4, it is covalent in nature. So ionic chloride means ionic compound. So it is PbCl2, that is lead dichloride is ionic in nature. Like these questions are important in the examination. Next, in SAF6 2 minus and SaCl2 Cl6 2 minus, which is known and why. SAF6 2 6 minus because of small size of fluorine is correct. SAF6 2 6 because of large size of fluorine wrong. SaCl6 because of small size of fluorine wrong. So large size of fluorine. So answer is, we can say SiF6 is known because of small size of fluorine. Because of small size of fluorine. Answer is first option only. SaCl6 is not known. Next question. Which of the following oxygen states are most characteristic for lead and tin respectively? Plus 2 and plus 4. Straight away we can say not plus 4 and plus 2, plus 2 and plus 4. So they are given both the options. Let us see the answer. Is option A, because plus 2 and plus 4 is correct. Most characteristic for lead and tin respectively, because tin and lead, tin plus 2 and lead plus 2 compounds are ionic in nature, whereas tin plus 4 and lead plus 4 compounds are covalent in nature. So this is a major difference. So which of the following oxygen states are the most characteristic for lead and tin respectively? Plus 2 and plus 4. Next continuation. So these are the important thing we have discussed. So next we'll discuss some more questions. I'm sharing new slide so that you can easily understand. So now I'm writing some more questions based on general properties. So please make a note. Some more questions based on general properties of 14 group elements, because some questions discussed is also very important here. I'm taking whiteboard and then I'm sharing only few questions since we have done up to example 5. Now we'll discuss example 6. Sixth question, question number 6. At least 10 questions if you discuss it will be better. Carbon forms. Carbon forms a large number of compounds. Carbon forms a large number of compounds due to option A, tetravalency, option B, it is variable valency, option C, it is large chemical affinity, large chemical affinity, and option D, it is due to property of catenation. So already you know what is the answer. It could be property of catenation. Because of catenation only it forms long straight chains, branch chains, and ring structure. So answer is straight away we can say it is due to catenation property. So option D, due to catenation property. Next question number 7. Question number 7. Producer gas is a mixture of producer gas. Producer gas is a mixture of option A, it is carbon monoxide plus nitrogen. Option B, it is nitrogen plus hydrogen. Option C, it is carbon monoxide plus hydrogen. And option D, it is carbon dioxide plus water. So what is the right answer? Producer gas, it's a mixture of carbon monoxide plus nitrogen. Answer is A, and this mixture is called water gas, syngas. Also water gas or syngas. So this is called producer gas. Answer is here, this first option, not C option. This for our understanding, I have written this also. Try to understand. Next question number 9. Let us start question number 9. So based on general properties only I'm writing. Which of the following, which of the following is a good conductor of electricity? Good conductor. The following is a good conductor of electricity. Option A, it is diamond. Option B, it is graphite. Option C, it is coal. And option D, it is coke. So which of the following is a good conductor of electricity? Straight away we can say carbon. These are the two crystalline isotopes of carbon. And in this, the graphite is conductible, diamond is not conductible. And these two are amorphous. This is the amorphous forms of carbon. And these two are crystalline forms. And diamond is a bad conductor of heat density. So crystalline allotropes and amorphous allotropes. And diamond is a bad conductor of electricity, whereas graphite is a good conductor of electricity. Graphite is a good conductor of electricity due to layer-like structure and containing free electrons. As it contains free electrons, good conductor of electricity. As it contains free electrons, because carbon undergoes sp2 hybridization in graphite, whereas in diamond it is undergoing sp3. Next question. Question number 10. This question is very important, ninth question. Many times they'll ask. Next question. The element which forms only one hydride is, only one type of hydride is. Option A, it is carbon. Option B, it is silicon. Option C, it is germanium. And option D, it is tin. So the right answer is carbon, because carbon will form only one type of hydride, that is CH4. Carbon can form only CH4. Silicon, germanium, tin can form other hydrides also, but carbon alone can form only one type of hydride, that is CH4. Next question, question number 11. Question number 11. Carbon shows tetravalency due to carbon shows tetravalency due to option A is sp3 hybridization. Option B sp2. Option C dsp2. And option D all of these. So it shows tetravalency due to sp3 hybridization only, as we already know. In fact, S4 for sp2. It will not undergo dsp2 because there is no d electrons present in carbon. So carbon cannot form dsp2 hybridization. because there is no availability of d electrons in carbon. Next question. Next question. The product of the following reactions. The product of the following reactions is R. Silicon dioxide combined with carbon on heating forms products. So the products are option A, silicon carbide and carbon dioxide. Option B, silicon oxide and carbon monoxide. Option C, silicon carbide and carbon monoxide. And option D, silicon and carbon monoxide. And means plus. So you can write anything. So the product of the following reaction are silicon carbide and carbon dioxide, silicon and silicon oxide and carbon monoxide. Next we have silicon carbide and carbon monoxide. So answer is third option, that is silicon carbide and carbon monoxide. This reaction is very, very important. So these are the questions we want to discuss. So I have discussed all the questions which I felt it is important. So with this, I'm ending this session. And all the general properties of 14 group elements are important. So please follow what we have discussed and do questions more on general properties. So try to solve more questions by using the slides and easily you can get the answers. Thank you all.